Howdy. There's quite something going on all over the place. Probably have noticed. I didn't have yet time to check out the sun. There might or might not be a CME coming. We have to see. But anyway, nature, that's from yesterday. That's rather new. News and views. 19th January 2023. Unconventional traces show that spring waters on Mount Fuji run deep. A trio of tracers has debunked the long-held model of the origins of spring water on Mount Fuji, revealing interactions between shallow and deep aquifer layers, and providing a fresh approach for probing mountain groundwater flow. Mountain water? Anyone? Mountains have been described as the water towers of the world. They receive large amounts of precipitation. Store snow and ice in their high altitudes mean that the water undergoes only low levels of evaporation and transpiration. Mountain rivers are crucial water resources both for mountain inhabitants and for downstream lowland populations. Groundwater stored in mountains is now recognized as an important water resource, but our understanding of groundwater flow paths in mountains is limited by a lack of field data, by the shortcomings of conventional access through your institution. So we cannot read any further than this. But anyway, we cannot read maybe 10% of the paper, or we can read 10% or maybe even less. That's just, I don't know how long this is because we don't have access. But it doesn't seem to contradict with mountain water at all. So since we cannot talk about that more because there's nothing to see and nothing to read yet, let's check out something else which, in my opinion, has very much to do with this same theme. We are talking about mountain water still. Earth as a capacitor in space, Earth's electrical circuits, and stuff. So that's also some news, I think, from today. Weather phenomena. Switzerland. Minus 42.3 degrees. That's why it got so cold in the Bernese Oberland. Colder Sagistalsee. On Friday night, it was very cold in the Bernese Oberland. We explain why the temperatures in so-called cold air lakes are so extreme. The Samtiser See is a closed cold air lake. On Friday night, the thermometer showed 70.8 degrees. That's what's about. From Thursday to Friday, there was a very clear night in Switzerland. That's why the thermometer showed extreme minus temperatures in certain places, especially in so-called cold air lakes. Temperatures fell well below minus 30 degrees. For once, it wasn't La Brevin. I have been there. In the canton of Neuchâtel, that was the coldest place in Switzerland, but the region around the Sagistalsee in the Bernese Oberland. The thermometer showed minus 42.3 degrees on Friday night because the lowest temperatures in Switzerland do not occur on the highest peaks in our country, but in so-called cold air lakes. Because the lowest temperatures in Switzerland do not occur on the highest peaks in our country, but in so-called cold air lakes. I just wanted to emphasize this. On the website kaltluftsee.ch, the phenomena of the cold air lake is described as follows. An accumulation of locally formed cold air in closed concave terrain or at obstacles as a result of cold air accumulation. A cold air lake is a collection of cold air in a depression in the ground. The phenomena often occurs in mountains. Did you know already? Yes, I knew. And I think I probably learned about the whole thing a bit more in recent times. Cold air lakes form mainly at night when the Earth's surface and thus the air directly above it cools down. On a mountain slope, this cold air flows down and can accumulate in depressions or other obstacles. On a mountain slope, this cold air flows down and can accumulate in depressions or other obstacles. What is also special about it is that in the area of cold air lakes, very different temperatures can be found within very short distances. In extreme cases, the temperature difference can be 30 degrees. Closed and open cold air lakes. The distinction is usually made between two types of cold air lakes. On the one hand, the closed, and on the other hand, the open cold lake. The Portal Kaltluftsehen here writes, basically a distinction can be made between, yes, the third time now. Closed cold air lakes are sinks with no surface outflow. Open cold air lakes are valleys that have a narrowing behind which the cold air produced can accumulate. There are several cold air lakes in Switzerland. By far the coldest on Friday was the Sägistallersee in the Bernese Oberland. The Grappellensee Alt St. Johann in the canton of St. Gallen made it to minus 30.2 degrees. Not far from the Grappellensee is the Samtisersee, beautifully embedded in the Alpstein Mountains. There the thermometer showed minus 17.8 degrees. This topic is yes. But anyway, there has been this Kaltluftsehen.ch, which is here. Do we get any? Yes, there's a translation. It's maybe not the front page. It's very interesting. They are on the right track. Everybody emits electromagnetic radiation. The type of radiation depends on the body on one hand and its temperature on the other. The higher the temperature, the more intense radiation emitted. If there is a temperature difference between two substances or body, energy in the form of heat always flows from the warmer to the colder body. The warmer body thermally stimulates the colder one. It absorbs energy, the particle movement of the colder body increases and the temperature rises. Conversely, the warmer body loses energy, its particle motion slows down and it cools down. There is some text to read. Let me go up to the menu, home page. Yeah, there is like this menu, you can check it out. Geomorphical factors. What's that? I haven't checked this out yet. In addition to the variable meteorological disposition, no wind, clear sky, loose layer of fresh snow, air mass that is cold as possible, there is also static disposition, which is given by the shape of the terrain. Charge accumulates on peaks. So we have to probably think of this lake being the opposite of a peak downwards, which could also have influence, or which quite likely has an influence on the electromagnetics in the region. If you have a high peak, you have maybe more positive charge accumulating on the peak on top of the mountain, and if you have a lake, which is probably even connected to very deep waters, it has, so to say, very deep roots, as probably Mount Fuji has, and many, many others. Like, this is one very crucial thing when you think about what I have been talking about, mountain water. If you don't know what I mean by mountain water, I will put a link below to the playlist. There's some, more than 300 videos about the topic. Probably you will find some answers. If you don't, ask me, and if I'm lucky, there's like even my paper coming out in some time from here. I'm waiting since some time it would come out. It would be easy to refer to that. But anyway, in contrast to the open cold air lakes, these have no cold air outflow in the region, in the area of the lowest point where the coldest air comes to rest. They are therefore favored for the occurrence of extremely low temperatures. Let's imagine this would be a mountain. Let's imagine this would be layers of temperature or air layers where we have different kinds of temperatures. If we have, like they said earlier, and something I read just before, that the cold air goes down the slopes of the mountain, which would mean that on the top of the mountain, let's say we have minus 30 degrees. And down here we have our lake. So the temperature of minus 30 degrees, you would think it would go down and it would stay minus 30. Or it could even warm up, you know? In a way, you would think so, like, because if you go to the valley down there where the people live, it's not that cold as on the peak of the mountain. That's why the mountains are usually covered in snow, because it's much colder up there. So how is it possible that there is, let's say, minus 30 degrees on top of the mountain, and then we go down to the lake and we have minus 42.8 or whatever here in the valley, or where the lake is? And if we would imagine we go still further down to the valley and we have houses and streets and cars, just imagine this would be a car. There we have, let's say, 10 degrees. I run out of space here on this screen. 10 degrees. So how is it possible we have minus 30 here, minus 42.8 in the middle, and 10 down here? I think the reason is in electromagnetics. This is Google Earth. Here we have the Sagittalersee. This is the volcano earthquake application. Earthquake filter. So we are watching at 7 days of quakes. So now let's check it out. There hasn't been any quake there near. The closest quakes might be those here, but what we are watching is this region. Here is somewhere the Sagittalersee. That's the Sagittalersee. It has a rather interesting shape. It isn't round like many others are. And it has either inflows or outflows. Maybe it doesn't have even an outflow. These wells are originating, they probably go into the lake, I think. Here on the other side we have also two, and they seem to come from these blurred out glaciers. Yeah, they stop here, at least this one stops here. So this doesn't have really an outflow, this lake, obviously. It is otherwise a very interesting region, but let's go back to Google Earth. I just wanted to show you that there wasn't any quake in the vicinity recently, because it was the first thing I was checking. So now let's have a look at it. Beautiful. Very nice tetrahedrons. Here we can see also layering. And I know Andy Hall. There seems to be something. Maybe slipped downhill once. Here is some region which has its distinctive look with those lines, shockwave formations, and here in the middle there isn't, like, it's completely different. You can see the distinction. There's a region here and here. That's different, and that's different. Do we have some other pictures? Yeah, there's another lake. No, that's in the background. I think that's Brienzersee or something. I don't know. We can see the color of the lake, that we have to think that there's probably quite some gypsum in it. That's the Sagitaler, and there is no outflow. There's no outflow in that. But we can also see that there's like this kind of gravel here and rather white looking stone rocks. Sun is rising or sinking. So now let's take this picture. Let's say on this peak there is accumulating positive charge, and if this is going basically down like this, we have negative. So if there is some atmospheric occurrence where magnetics, like weather, is electric totally. We had solar flare activity and all these kind of things recently. Maybe there's, no, not maybe, there's much more coming. So let's try to make still some videos as long as we have internet and stuff. Well, anyway. And if there is a charge in this lake, where probably there is, it will attract charges from above, and it will make this kind of magnetic vortex. So which could make this kind of tunnel, which goes upwards, and it makes a connection to somewhat much higher atmospheric layers, which then also pull down cold air exactly to the place of the lake. It makes this kind of antenna which goes upwards. Because it's this kind of negative thing. It might be a crater, it might be a caldera. There might be one day when there is like a whole lot of water coming out of that lake. And everybody gets surprised. How is it possible? Charge accumulates in peaks. That's why there are mountain tops which are getting hit by lightning very often. That's why you shouldn't stand under a tree if you're outside and there is a thunderstorm coming, because the possibility of the lightning strike hitting this tree, which if there's like just one tree and you're standing on the field and you go to the tree, and if there's a lightning strike, the possibility that the lightning strike hits this tree is very big, because it is elevated. The charge accumulates on the edge of the tree. The same principle is somehow applied here. That's already some days old. I didn't manage to make a video. Deflecting lightning with a laser lightning rod. In tests conducted on the summit of the Santis, a scientist found that the discharge could follow the laser beam from several dozen meters before reaching the tower of the operator Swisscom. And I don't know if that's a real picture or if this is just some computer animation. I don't know, this looks really a bit odd. Forest fires, power cuts and damaged infrastructure. Lightning fascinates and destroys in equal measure, causing as many as 24,000 deaths every year worldwide, not to mention widespread destruction. Even today, the lightning rod invented by Benjamin Franklin is the best form of protection, and yet these rods do not always provide optimal protection for sensitive sites. A European consortium consisting of the University of Geneva, École Polytechnique, Paris, EPFL, Hesse, Sceaux and Trumpf Scientific Lasers München has developed a promising alternative, the laser lightning rod, or LLR. After testing the LLR on the summit of Santis in Switzerland, the researchers now have proof of its feasibility. The rod can deflect lightning over several dozen meters even in poor weather. The results of this research are published in the journal Nature Photonics. Lightning is one of the most extreme of natural phenomena. An abrupt electrostatic discharge of millions of volts and hundreds of thousands of amperes. Lightning can be observed in a single cloud, between several clouds, between a cloud on the ground, and vice versa. As fascinating as it is destructive, lightning is responsible for... We had this already. Lightning protection devices have changed little since 1752, when Benjamin Franklin invented the lightning rod, a pointed conductive mast made of metal connected to the ground. A traditional rod is to this day still the most effective form of external protection. It protects a surface with a radius that is more or less equal to its height. So if a 10-meter rod will secure an area of 10-meter radius, however, since the height of the masts is not limitlessly extendable, it is not an optimal system for protecting sensitive sites over wide areas such as an airport, wind farm, or nuclear power plant. Making the air conductive, an European consortium led by UNIGE and École Polytechnique Paris has been looking out how to solve this problem in close partnership with Epifil Lab, Professor Farmarachi, Trump Scientific Ariana Group, AMC, name dropping. It has been working on a device known as the laser lightning rod, LLR. By generating channels of ionized air, the LLR was used to guide lightning along its beam. Extending upwards from a traditional lightning rod, it could increase its height virtually as well as the surface of the area it is protecting. When very high-power laser pulses are emitted into the atmosphere, filaments of very intense light from inside the beam, begins Jean-Pierre Wolf, full professor in the Department of Applied Physics and Physics section of UNICH Faculty of Science and the Studies last author. These filaments ionize the nitrogen and oxygen molecules in the air, which then release electrons that are free to move, continues Professor Wolf. This ionized air, called plasma, becomes an electrical conductor. Tests at an altitude of 2,500 meters, the LLR project meant that a new laser had to be developed with an average power of 1 kilowatt, 1 joule per pulse, and a duration per pulse of 1 picosecond. The rod is 1.4 meters wide, 8 meters long, and weighs more than 3 tons. This terawatt laser was tested on the summit of Santis in Appenzell at a height of 2,502 meters, already instrumented by Epifil to observe the lightning. Anyway, this is getting already much too long. Read the rest of it, and I leave it here. This could be very long. Thanks. Bye. I will stop now here because this will be endless, and I'll probably run out of memory space and such things. But anyway, read the stuff and think about it. That's all you need to do if you're whatever.